Welcome to the presentation on HV switchgear, high voltage switchgear. So the contents what we will see is HV switchgear and control gear datasheet. So the standards on which we will touch upon in today's presentation will be IEC standard 62271. Then we have IEEE standard and ANSI standard. So the terminologies what we will define today shall be both as per IEC as well as IEEE perspective, so that any project across any geographical location would be easy for understanding the presentation. So the typical IEC standard for HV switchgear design, first is 62271, which is the fundamental standard for IEC, which is high voltage switchgear and control gear. It has its other parts 100, 200 for switchgear and circuit breaker, which we will discuss later. Then we have 60282 part 1 for high voltage fuses as well as current limiting fuses part 1. Then we have IEC 60470. This is for high voltage alternating current contactor. Then 60529, irrespective of HV and LV, it is for the enclosure protection IP rating. Then IEC 60282 for high voltage fuses and 60265 for high voltage switches. Similarly, for ANSI and IEEE standards, we have C3720.2 IEEE standard for metal clad and station type cubicle switchgear. We have ANSI C3706, which are high voltage circuit breaker rated on symmetrical circuit basis, preferred rating and regulated requirement capabilities. So basically these standard ratings of each switchgear and its components are mentioned in this ANSI standard. C3700 for the typical standard definition of a HV switchgear. C37.46 for the specification of fuses and fuse disconnecting switches. And finally C37.53.1 for high voltage current limiting motor starter fuses and its test procedures. Now, first and foremost important, while we are discussing or understanding HV switchgear, we should know that the range of HV switchgear, that it starts from which range and it can be extended up to which particular range. So as per IEC 62271 part 200, which is for high voltage switchgear, clause 4.1 will say the standardized voltages in kilovolt are 3.6, 7.2, 12, 7.5, 24 and 36 kV. Similarly, the range of high voltages mentioned in IEEE C 3720.2 clause 5.2.1 are 4.76, 8.25, 15, 27 and 38. So while projects can happen across any geographical locations across world, it is essential to understand that we are working on which standard, whether it is IEC standard or IEEE standard, because based on these two standards, as you can see, the voltage ratings vary a lot. So it should not happen we are working for an IEC project and we are selecting the high voltages based on the IEEE rating and vice versa. Secondly, the rated frequency. So as per IEEE 62271-200 clause 4.3, HV switchgear can be built or designed based on two frequency options. First is 50 and 60 Hz. There are certain options where we can go for 16.67 or 25 Hz. So these are optional frequencies. However, for IEEE C 37.20.2 clause 5.3, the rated frequency is 60 Hz, optional is 50 Hz, because IEEE and ANSI are mainly related to North American and Canadian applications. So where 60 Hz is the standard operating frequency of the system. Then short time withstand current or the fault current rating standard. As per IEEE IEC 62271 part 200 clause number 4.5, the values of short circuit breaking capacity, mind it. So the capacity at which during fault the circuit breaker or the short circuit protective device can break the fault current are 6.3 kiloamps, 8 kiloamps, 10 kiloamps, 12.5 kiloamps, 16 kiloamps, 20 kiloamps, 25 kiloamps, 31.5 kiloamps, 40 kiloamps, 50 kiloamps, and 63 kiloamps. So one thing to note is while IEC or any standard specifies a variety of range of the ratings of any short circuit rating or any voltage rating, while we are selecting a component, we have to follow the OEM, that is the original equipment manufacturer or vendor's catalog, to check whether the equipment which we are selecting is really available for the rated capacity or not. For example, let's say if I am selecting 50 kiloampere fault current or short circuit rating for an HT switchgear of 3.3 kilovolts, it may happen that many manufacturers do not have their standard manufacturing range of 50 kiloampere for 3.3 kV rated HT switchgear. So in that case, it is very essential to see that which manufacturer will provide me a standard type tested with all available proper type test reports 50 kiloampere rated short circuit breaking capacity for my 3.3 kV switchgear. So this is also a very important point which I wanted to touch upon. The short circuit rated breaking capacity for ANSI C3706 table 1 mentions 16 kiloampere, 20 kiloampere, 25 kiloampere, 31.5 kiloampere, 40, 50 and 63 kiloampere. So if you look, there is a clear line of similarity from 16 till 63 for both IEC and ANSI designed switch gears. However, as you can see for ANSI, 6.3 up to 12.5, this small range short circuit breaking capacity is not available in the ANSI standard. Then the rated short circuit duration. The first earlier slide what we discussed was about the rated short circuit current, that is the breaking current. Now the withstand time for which the fault can withstand in the system or the equipment. So as per IEC 62271, clause 4.7 clearly mentions the standard value of rated duration of short circuit is 1 second. So up to 1 second, the short circuited force will be okay, to withstand the integrity of the switchgear. There should not be any problem. If it is necessary, a value of lower or higher than 1 second can be chosen. The recommended values in those cases shall be 0.5 second, 2 second and 3 second. So the standard rating IC mentions is 1 second. But if you have to choose something lower or greater than 1 second, those values are also recommended and clearly specified. Means we cannot choose any arbitrary value while selecting the short circuit duration of the HT switchgear as per IC. However, IEEE 3720.2 clause 5.4.5 clearly mentions that the rated short circuit duration is equal to 2 seconds. So you do not have an option to lower down or go high. So see students, while we are discussing about these particular presentations, you can see that IEC offers a little bit more flexibility or gives more option for an user to select the specific equipment ratings. While in many cases IEEE standardizes the rating for the switchgear. So both has their own pros and cons, which we can discuss in some other presentation. But while a new project will be designed, if someone has to argue, or there should be a healthy discussion between whether to choose an IEC or an IEEE standard for HT switchgear. So this thing we have to keep in mind that IEC always offers a wide flexibility of options to select from, whereas IEEE has relatively less options and they are mostly standardized in majority of the cases. The control power source. So we all know that apart from the main rating, there are control supply voltages which we have to derive from multiple sources. So those control voltages are also clearly specified and standardized both in IEC as well as in IEEE standard. While IEC 62271 part 100 clause 4.8 mentions for direct current DC, the standard control power voltages shall be 24, 48, 60, 110, 125, 220 or 250 volts. And for AC, it could be 120, 220, 230 or 240, which can be tapped either through a control transformer or through a direct line to neutral tapping. Control transformer for HT. And ANSI C3706 table 8 mentions for auxiliary circuit the direct, for if it is direct current, it should be 24, 48, 125 and 250 volts respectively. And for AC, it will be 120 and 240. So from here also you can see that IC has a wide range of options to select from, whereas relatively compared to IC, the options are less for ANSI or IEEE rated HT switchgear standard. Now, what will be the standard insulation voltage or insulation level for the HT switchgear? So, IEC 62271 clause 4.2 clearly mentions for the standard voltages what are the rated lightning withstand voltage and power frequency voltage, right? And for ANSI C3720.2 table 1 will mention for the ANSI standard voltages. So 3.6 40 kV is the lightning withstand voltage, whereas 10 kV is the power frequency withstand voltage. For 7.2 60 kV is the rated lightning withstand voltage, 20 is the power frequency withstand voltage. And as you can see, as the voltage level increases, the insulation power frequency voltage and impulse lightning impulse voltage both increases based on the voltage ratings. Similarly, for ANSI standard, you can see from 4.76 through 38 kV, the rated lightning voltage varies from 60 till up to 150 kV and power frequency from 19 kV till 80 kV. And you can see one thing here surprisingly that for 8.25 and 15 kV, these two voltages, the power frequency withstand voltage and the lightning impulse voltage, both the values are same, which is 36 and 95 respectively. So these are very, very important that whenever we review a data sheet or we prepare the specification of any HT switchgear, we have to specify clearly the power frequency and lightning withstand voltage, which we have to take it from the standard IEC and ANSI standards. And vendor has to abide that. Now we are moving to the constructional aspect of the switchgear. So when we say the constructional aspect, first and foremost thing that comes to our mind is the enclosure part. The enclosure in which the HV switchgear components will be designed and constructed. So first thing, there are two types of construction in switchgear. One is called the metal clad switchgear. Second we call is the metal enclosed switchgear. Now let us try to understand the difference between metal clad and metal enclosed switchgear. So as you can see, the interrupting device in metal clad can be a draw out circuit breaker, but in case of metal enclosed, every switching components and switchgear components will be enclosed in a housing. So therefore you cannot use a draw out type switchgear circuit breaker. You have to use a fixed switch and fuse unit. The buswork for metal clad will be insulated type. For metal enclosed, it will be bare type. The live parts are not exposed when the cover is removed, but in metal enclosed, if you remove the barrier or the cover, the live parts, let's say the bus bar and everything will be, the operator will be exposed to. The cost of metal clad will be high and metal enclosed will be low, because you can see the bus works are insulated, draw type circuit breakers can be done, then you have a barrier when the cover are removed. So all this adds cost to the construction design of the switchgear. So as a result, the cost will be definitely high for metal clad versus metal enclosed switchgear. The maintenance, because of its little complex construction and more detailed construction or more safety features added to it, will be high for metal clad, relatively low for metal enclosed switchgear. Auxiliary power requirement will be yes for metal clad, for metal enclosed not required. Auxiliary power, let's say for racking and racking out of the circuit breaker, you would require a control supply voltage. Since this doesn't provide an option for that, so therefore for this particular option, there is no requirement of the control supply voltage. So the duty cycle will be high for metal clad and low for the metal enclosed switchgear. Now what are the applications for metal clad? This is most suited for demanding medium voltage applications, which require little rugged operation, little sustained or operator related operations. So their metal clad is most promising or most choiceable for the users. And this metal enclosed are suited for less demanding medium voltage applications. For example, where there is no operator required every time, where you want to reduce the overall cost of the switchgear but want to keep the integrity of the design, there you can go for a metal enclosed switchgear. So the last sentence, which is very important to understand and never forget this difference, which I personally also do many a times, that metal clad is metal enclosed, but metal enclosed is not metal clad. What do I mean by that? You can see all the characteristics of metal enclosed are somewhere included in part of metal clad, but the specifications of metal clad are not part of the metal enclosed. So this is how you can remember what is metal clad and what is metal enclosed. This is highly confusing many times, but if you can remember in this way, I think it will be very difficult for you to forget in the coming times. Now, as we are deep diving into the constructional aspect of the HV switchgear part, firstly, we have seen the overall construction or the enclosure part. Now we will look into the feeder breaker configuration. That is, the heart of a switchgear is always the circuit breaker, irrespective of any voltage. So now we have to see how the breakers are installed in the HV switchgears. So this is a door opened side constructional view of a MV switchgear or HV switchgear. So this is a mid-high cassette type switchgear, and this is a trolley type, which is a metal clad type switchgear. So here you can see this is the circuit breaker component. So here there are wheels. So this can be racked out and this can be racked in for disconnecting the circuit breaker. But in this particular case, this is a cassette type, so you cannot totally make the circuit breaker compartment out of the system. So as you can see, there are two types of construction. Here, after the disconnecting part, the jaws of the breaker units are closed. There are shutters to provide safety of operation. And this is view B. The shutters are open so that the racking is possible. So this part you can see, this is the circuit breaker front fascia. This is the circuit breaker rear fascia. So these are the 6 jaws which will go and connect in this particular point to couple the circuit breaking assembly. Okay, this is a typical construction which you can see for a IC MV or HV circuit breaker for a HT switchgear. Now for IEEE, again the construction varies a little bit. So if you can see here, these are metallic shutters which closing the jaws of the breaker. And once this is open, this is the view B, where you can see the open jaws, where the circuit breaker jaws will get racked and get coupled to this for making it connected to the system. So this is again the racked out front view of a circuit breaker, MV circuit breaker, and this is the rear view of the MV circuit breaker.